Good morning, my name is Patrick Robinson.
I'm Kayana, Blanchard.
And my name is Engstrom.
And we're going to be talking to you today about our multiple distilled solar distiller.
Human life sustainability depends mainly on water. However, access to potable water to people are down and down day by day. 85% of the world population lives in the driest half of the planet. 783 million people do not have access to clean water. And nearly 2.5 billion people do not have access to adequate sanitation. Most of human diseases are due to polluted or non-purified water sources. 6 to 8 million people die annually from the consequences of disasters and water-related diseases. Therefore, water purification without affecting the ecosystem is the need of the hour. Our objective is to provide clean and accessible water to the people in need. Our device will be a multiple basin still system that uses the process of solar distillation to purify water. Though there exist many devices in the market, we are looking to optimize single-day productivity while minimizing costs. It should not require or depend upon any external power sources. Our unit should cost approximately $50 while producing up to 3 gallons of water daily to support a household of 3 people. It should also require minimal user interactions, lightweight for ease of handling and shipping.
So there are some current market competitors. We have the Solar Ball, which is very similar to ours. The Solar Ball is a dual still system. Their output that they are proposing is 3 liters. They're still in design phase. They are also using evaporation to go ahead and clean and desalinate the water. There's also the gravity filter. Gravity filter you can purchase. The issue with the gravity filter for us is that it does require a filter, which in case does have to be changed. Now this filter can be changed, but for our output it will be changed every 4 months. So every 4 months you have to spend money to keep your system. The last one is the Life Straw. Uses the 0.2 micron filter, and this one, as previously stated, has the filter in it. Now this filter cannot be changed. You have to replace the unit. The unit does last for a while, but with our water output, it would last roughly 6 months. So some of the related standards we're using ISO, NSF, and ASTM. These are going to be the methods for the solar transmittance, also the moisture effects on heat transfer, and the sizing and the direct weathering on our unit.
This is our Gantt chart. As you can see, we're in April. We're finished with our preliminary design and our material research phases. As we start May and into the summer, we're going to be going into our research and simulation stages. We'll be using software like SolidWorks or ANSYS in order to design a unit on a computer. And we're also going to use practical experimentation like scale models or compartmentalized models in order to find more specific design characteristics. Our final prototype is expected around November, early December timeframe, and it should have all the characteristics we're looking for. These are the design parameters. The shape and the material of the still are the primary considerations. We're looking at a large rectangular shape with a slanted roof in order to optimize our air volume to saturation levels, and the slope will enable us to capture all the precipitation and channel it into the reservoir. Same thing with the brackish water depth. That's very important because it helps optimize the surface level of the surface area of the water versus the volume of the water. That way we have a good heat transfer through that. Cohesive seal to prevent vapor locking, as well as the cover slope and insulation. That is to optimize efficiency.
During our research phase, we analyze factors that could have an effect on the overall efficiency of our unit. They are the effect of surface area on productivity, internal air circulation, material selection, overall thermal efficiency, and the economic impact. Selecting the proper material is vital for an efficient unit. So they should have the following characteristics. They should have high durability and portability, low cost and low toxicity, and high local availability. So far, we have chosen to use preformed polyethylene plastic for the basin due to its low cost, long life, and easy cleanability. Tempered glass for the cover due to its low absorbing and reflecting properties, and black high temperature silicone rubber for sealing to reduce heat loss.
So when it comes to our system, we had to use an iterative process to go ahead and size our system to allow for 1/2 to 3 gallon output. From there, this process was to increase the surface area while decreasing the volume of our system in whole. Some of the inputs were the area, the output desired water output, also the outside temperature of the location. Since we are going to be testing here in Florida, we're using Florida, but we are trying to keep this same equatorial region with our unit. Another one is the insulation and also the effects of condensation, conduction, and convection. So for our prototype, we're using a 10-basin still system. From here, this is going to increase the surface area to volume ratio. As this ratio is increasing, it allows the water to increase in temperature faster. As the water temperature increases faster, the humidity ratio increases, which in turn allows for the evaporation to work faster. The faster the evaporation occurs, the more output that our system can have and maintain. As we have a 11th channel, which has our floater valve, the floater valve is pretty much there to regulate our system because we do want to keep our system with as minimal water in these basins as possible. We do not want to flood the system to where we just have all 3 gallons in there at once. So this floater valve will go ahead and actuate whenever our evaporation is happening. The floater valve will actuate, allowing water to go in, filling up our stills as the water level increases to the desired level. Then from there, the floater valve shuts off and then the process occurs again. As the water evaporates, it will condensate on our slope, which then goes to the front channel, which is our collection channel.
The economic aspects. It comes down to 3 components that will all be used to evaluate the actual cost over its lifespan per unit size. That's for our design. The size, quantity being constructed, and materials used will have a more economically viable effect the larger the unit is. So it'll be able to produce more water for less cost per unit. However, that's conflicted by the construction, transportation, distribution costs, which the smaller the unit is, the easier it's going to be to transport and get to where it needs to be. So there has to be some kind of a balancing act there. We'll have to optimize for its maximum cost per unit size. The lifespan of the unit is going to have a multiplying effect on the actual lifetime cost of the unit, because the more years that it's able to produce water, the cheaper it's going to be per unit of water in its total lifespan. With that analysis, we'll be able to compare it to filtered units or other options that governments have reaching water for hard-to-reach places. And our ultimate goal is to have a durable unit that lasts long enough so that the total cost will be less than filtered competitors. By the nature of our unit and its target audience, the global initiative is all over it. The target market for our unit is developing countries in equatorial regions. Think sub-Saharan Africa, Indian subcontinent, South America, Caribbean. And it's with this target we chose to use a text-free user guide, so it'll be all pictographical. And then we also have instructions in English, Spanish, and Haitian Creole, and French. The goal, which was set earlier, will have no power, so this will be completely solar operated. It will use sun heat, so no electricity is required. And the ease of the system and minimal maintenance means that nobody needs to be trained or instructed on how to use it prior to installation. The application actually works for fresh or salt water, and it will even work for other saturated mediums, so foliage, mud, anything that has a high concentration of water will evaporate out, and then you'll be left with the particulate behind. So it has a universal characteristic of that.
So in conclusion, we've gone over how we actually sized our system, some of the economic analysis. We've also showed how we went with a rectangular design instead of the solar ball's hemispherical design, as previous papers have been written showing that rectangular designs are more efficient. And from there, we're trying to just maximize the evaporation rate with our unit. We'd like to open the floor for any questions.
I'd only make one comment. Your building of your prototype probably should be moved back a little bit to give yourself some time to fail and figure out something else to fix it. Or right now, if you're doing it in November and December, and we're back here December 15th, and you're still messing around with your prototype, you might be better off moving that back and give yourself some time.
Yes, sir, absolutely.
Along the same lines, fairly simple system because it doesn't have moving parts and things like this. And so whatever, my expectation would be that you would make a prototype earlier, you would do testing, and you come back in here and do some predictive modeling on what you expect it to do, execute the testing, and then come back and tell us that it meets it or why it doesn't. So we have an understanding that you've used the engineering tools that you've spent all these years learning. Okay. The economic side of it, you said cost of filtered water versus the cost of bottled water. Come back and give us a predictive model of how long it would take to pay back on this.
Yes, sir.
Net present value type of calculation, which is fairly easy to do. And then I assume where you say quality of water output, that you're going to do some level of chemistry
Yes.
on the water, the conductivity, the pH balance and all of that, so that we know that the purity of what your output is as good as you say it is.
Yes, sir.
And so those are my suggestions.
All right, thank you.